You reach out, you grab a cup, you pick it up, you put it down. Simple. You've done it 1,000,000 times. But here's something that's going to bother you. You never actually touched that cup. Not once. Not ever. Your hand got close. Very close. But the atoms in your fingers and the atoms in the cup never made contact. They pushed against each other from a distance. And what you experienced as touching was actually repulsion. Electromagnetic repulsion between electrons that never ever touch. You've never touched anything in your entire life. Now, before you say that's just semantics, that's just playing with words, let me tell you something. This isn't a trick. This isn't philosophy. This is what's actually happening at the level where physics operates. And understanding this, really understanding it, changes everything about how you see the physical world. Think about what touching means. You put your hand on a table. You feel solid. The table feels solid. Contact has been made. That's what your brain tells you. But zoom in. Look closer. At the atomic level, what's happening? The atoms in your hand have electrons orbiting around nuclei. The atoms in the table have electrons orbiting around nuclei. As your hand approaches the table, these electrons get closer to each other. And electrons repel. They're all negatively charged. Same charges push apart. It's one of the most fundamental rules in physics. So as your hand gets close, the electrons in your hand and the electrons in the table start pushing against each other. Harder and harder as the distance shrinks. And at some point, that repulsion becomes strong enough that you can't push any further without breaking something. That's what you feel as solid. That's what touching actually is. Electrons repelling electrons across empty space. The atoms never make contact. There's always a gap. Tiny, invisibly small, but real. Your hand hovers above the table, held up by electromagnetic forces, never actually touching. And this isn't special to tables. This is everything. Every time you've ever touched anything, picked anything up, felt anything solid, you were experiencing electromagnetic repulsion. Not contact, repulsion. You've been floating your entire life. Now you might be thinking, okay, fine. Technically my atoms don't touch the table's atoms. But so what? I still feel something solid. What's the difference? The difference is understanding what forces actually run the world. Because once you realize that solidity is just electromagnetic repulsion, you start to see that electromagnetism is everywhere. It's not some special force that shows up in magnets and lightning. It's the force that holds your body together. The force that lets you interact with objects. The force underlying all of chemistry, all of biology, all of material science. When you walk, electromagnetic forces between your feet and the ground push you forward. When you breathe, electromagnetic forces hold the molecules in your lungs together while allowing them to move. When you see, photons, particles of light, interact electromagnetically with electrons in your retina. It's all the same force, and it's all based on one simple fact. Charges interact. Positive and negative attract. Same charges repel. That's it. But here's what's remarkable. This one force, acting according to this simple rule, creates all the complexity you see around you. The hardness of diamond, the flexibility of rubber, the conductivity of copper, the transparency of glass. All of it comes from electromagnetic interactions between atoms. Different materials feel different, not because they're made of fundamentally different stuff, but because their atoms are arranged differently. And those arrangements determine how the electromagnetic forces between them behave. Let me tell you how strong electromagnetic forces are. Because people don't appreciate this, they think of electricity as something in wires and lightning. They think of magnetism as something in magnets, separate phenomena, special cases. No. Electromagnetism is the dominant force in your everyday life, by far. It's not even close. Compare it to gravity. Gravity is the force you think of as strong. It holds you to the earth. It keeps planets in orbit. It seems powerful. But electromagnetic forces are stronger than gravity by a factor of about 1 followed by 40 zeros. I don't even know what to call that number. It's not much stronger. It's incomprehensibly, absurdly, overwhelmingly stronger. So why don't you notice? Why doesn't everything just explode from these enormous forces? Because atoms are neutral. Every atom has positive charges in the nucleus and negative charges in the electrons surrounding it. The positive and negative cancel out. perfectly balanced. So even though the forces are gigantic, they hide inside atoms, neutralized. When you rub a balloon on your hair and stick it to a wall, you've moved a few electrons, just a few, a tiny imbalance. But the electromagnetic force is so enormous that even this microscopic charge separation creates an effect you can see across the room. That's how powerful it is. A few extra electrons on a balloon and suddenly it defies gravity, sticking to a wall. Now imagine what would happen if atoms weren't neutral. If there was even a small imbalance, the forces would be catastrophic. Matter as we know it couldn't exist. So the fact that you can touch things, that objects stay intact, that the world is stable, depends entirely on charges being balanced. Electromagnetism is the strongest force you experience, but it's hiding in plain sight, cancelled out inside every atom. Alright, so you know that touching is actually electromagnetic repulsion. But what's really happening? What does it mean for electrons to repel? Here's where it gets interesting and strange, because the way forces work at the quantum level is nothing like everyday experience. In classical physics, you'd say there's a field, an invisible field surrounding every charged particle. And when another charged particle enters that field, it feels a force. The field pushes or pulls on it. That's not wrong, it's a useful way to think about it. But it's not the deepest level. At the quantum level, forces are mediated by particles. When two electrons repel each other, what's actually happening is they're exchanging photons, virtual photons. One electron emits a photon, the other electron absorbs it. And that exchange, that transaction, is what creates the force you experience as repulsion. It sounds crazy. How does throwing something at someone push them away? If I throw a ball at you, you get pushed back when it hits. That makes sense. But how does exchanging photons between electrons create repulsion? The answer is quantum mechanics. At this level, particles don't behave like little balls. The photon isn't a ball being thrown, it's a quantum of interaction, a unit of exchange that carries momentum and energy. And the mathematics, the actual calculations, show that when electrons exchange these virtual photons, they repel. Not because we can visualize it, not because it makes intuitive sense, but because that's what the equations predict and experiments confirm it. You can't see these virtual photons, you can't catch them. They exist only during the interaction. They're called virtual because they don't have independent existence. They're created by one electron and immediately absorbed by another. But they're real in the sense that their effects are measurable. Every time you push on a wall, trillions upon trillions of virtual photons are being exchanged between the electrons in your hand and the electrons in the wall. And those exchanges create the force you feel as solid. Now here's something beautiful. All of electromagnetism, everything I've been describing, comes down to just three actions, three fundamental processes that combine in different ways to create all the complexity. First action, a photon travels from one place to another. That's it, light moving through space. Second action, an electron travels from one place to another, a charged particle moving. Third action, an electron emits or absorbs a photon. Interaction, exchange. Those three actions, that's the complete list. Everything electromagnetic is built from combinations of these three things happening over and over in different patterns. When you touch a table, electrons in your hand and electrons in the table are exchanging photons. Action 3, repeated endlessly. When light travels from the sun to your eye, that's action 1, photons propagating. When an electron moves in a wire, creating an electrical current, that's action 2. And when those three actions combine in more complicated ways, when photons bounce back and forth, when electrons move and emit and absorb, you get all of chemistry, all of optics, all of material science, the structure of matter, the properties of substances, color, transparency, conductivity, all of it. There's no hidden mechanism beneath this. There are no gears or springs or invisible machinery. This is the bottom level. This is how nature actually works. But wait, if touching is just electromagnetic repulsion, why can't you push your hand through a table if you push hard enough? Why doesn't the table just compress? Because there's another rule, a quantum mechanical rule that's even more absolute than electromagnetic forces. It's called the Pauli exclusion principle, and it says that no two electrons can be in the same quantum state at the same place. This is not a force. It's not electrons pushing against each other. It's a fundamental prohibition built into quantum mechanics. Two electrons simply cannot occupy the same state. They refuse. Nature doesn't allow it. So when you push on a table, you're not just fighting electromagnetic repulsion. You're fighting this quantum mechanical rule. The electrons in your hand cannot occupy the same space as the electrons in the table. Not because of force, because of law. This is why matter has volume. This is why you can't squeeze atoms arbitrarily close together. The exclusion principle creates an effective hardness that has nothing to do with forces in the traditional sense. Without this principle, atoms would collapse. Electrons would all fall into the nucleus. Matter as we know it couldn't exist. Everything would compress into an infinitely dense point. But nature forbids it, and that prohibition, combined with electromagnetic forces, is what makes solid objects solid. Now, if all materials are just atoms held together by electromagnetic forces, why do different materials feel so different? Why is steel hard and rubber soft? Why is glass transparent and metal opaque? Same forces, different arrangements. In steel, atoms are packed in a very regular crystal structure, very tight, very organized. When you try to deform steel, you're fighting against this rigid lattice. The electromagnetic forces holding it together are distributed in a way that resists change. In rubber, atoms are arranged in long chains that can slide past each other. The electromagnetic forces are still there, still holding atoms together within each chain, but the chains themselves can move. That's flexibility. In glass, atoms are arranged irregularly, not quite crystalline, not quite liquid, frozen in place but without long-range order. This particular arrangement lets light pass through because photons at visible frequencies don't interact strongly with the electrons. In metal, electrons are free to move. They're not locked to individual atoms. So when light hits metal, those free electrons absorb the photons and re-emit them. That's reflection. That's shininess. Same fundamental force, same three actions, just different configurations of atoms creating different macroscopic properties. Understanding this is one of the great achievements of physics. We don't need a different theory for every material. We have one theory, electromagnetism and quantum mechanics, and it explains everything from the hardness of diamond to the stretchiness of rubber to the conductivity of copper. Let me tell you how good our understanding of electromagnetism is. Because when I say we understand it, I don't mean we have some vague qualitative picture. I mean we can calculate with extraordinary precision. There's a property of the electron called its magnetic moment. How magnetic it is. Very small, very difficult to measure, but measurable. Using quantum electrodynamics, the theory that describes electromagnetic interactions at the quantum level, we can calculate what this magnetic moment should be. The calculation is horrendously complicated. You have to account for virtual photons being exchanged, for electrons emitting photons and reabsorbing them, for all possible ways the interaction can happen. But when you do the calculation and compare it to the measured value, they agree to 10 decimal places. 10! That's like predicting the distance from New York to Los Angeles and being accurate to the width of a human hair. That kind of precision doesn't exist anywhere else in science. Not in biology, not in chemistry, not even in most of physics. This isn't a rough approximation. This is nature being described with extraordinary accuracy. And it all comes from understanding electromagnetic forces. When you touch something, when you feel that solid resistance, you're experiencing a force that we understand better than almost anything else in the universe. So let me bring this back to where we started. You reach out, you grab a cup. What's actually happening? Electrons in your fingers are getting close to electrons in the cup. Close enough that they start exchanging virtual photons. Those exchanges create repulsion. The electromagnetic force pushes back against your hand. Your hand stops at a certain distance, not because atoms made contact, but because the electromagnetic repulsion became strong enough, combined with the Pauli exclusion principle, that pushing further would require breaking chemical bonds. That resistance, that sensation of solid, that's what touching is. Electromagnetic forces acting across empty space. You've never actually touched anything. The atoms in your body and the atoms in everything you've ever interacted with have always maintained a tiny separation. But those electromagnetic forces, those are real. Those are what you feel. Those are what let you interact with the world. And the remarkable thing is we understand these forces. We can describe them mathematically. We can predict what they'll do. We can calculate their effects to extraordinary precision. The same force that holds your body together, that keeps atoms from collapsing, that creates all of chemistry, that makes objects solid, is the force you experience every time you touch something. It's not mysterious, it's not hidden, it's the most obvious force in your life. You just didn't realize it until now. So next time you pick something up, think about what's really happening. Your hand hovering above the object's surface, held back by electromagnetic repulsion. Trillions of virtual photons being exchanged every second. Electrons pushing against electrons across empty space. You're not touching it, you're feeling the electromagnetic force. The same force that runs the entire universe. The same force we can describe with equations that match reality to 10 decimal places. And the fact that something so fundamental, so powerful, so precisely understood is what you experience as the simple act of touching something. That's not disappointing, that's extraordinary. Nature isn't hiding, it's showing you directly what it is. Every time you interact with anything, you're experiencing fundamental forces. You're doing physics. The world isn't less interesting because we understand it. It's more interesting. Because now you know what you're actually feeling. Now you know that solid isn't solid, that touching isn't touching, that empty space between atoms is where all the action happens. That's what's real. That's what you've been experiencing your whole life. And now you know.